Hello friends, welcome back to Pharma Health Insights for quality, compliance and success in pharma. In this masterclass, we will discuss real GC troubleshooting problems that analysts face during routine pharmaceutical testing. These are not theoretical concepts but real laboratory issues that directly affect analysis, documentation and batch release. For each problem, we will understand what is observed, why it happens and how it can be corrected practically in the laboratory. So, let us begin with the most basic and most alarming GC problem. When this problem occurs, the injection and the run appears normal, but no peaks are observed on the chromatogram. This clearly indicates that the sample is not reaching the detector. The first check must always be the carrier flow gas. Without gas movement, the sample cannot travel through the column. Next, confirm the injector temperature has reached and stabilized at the set value. Improper vaporization prevents analyte transfer. Then inspect column connections at both injector as well as the detector ends. Loose fittings or broken column tips are very common issues. Finally, confirm that the detector is switched on, ignited and stabilized. Once peak begins to appear, the next commonly faced problem is the reduced response. In this situation, peaks are present, but their response is significantly lower than expected. This problem commonly occurs due to injector-related issues. An aged septum allows sample vapors to escape. A contaminated liner absorbs analyte, reducing response. High split ratio further decreases the amount of sample entering the column. Therefore, injector components should always be checked first. Replacing septum and liner solves these issues in most routine laboratory cases. Now that the response is adequate, the next issue analysts commonly observe is abnormal peak shape. Peak tailing indicates interaction between analyte and active sites within the GC system. This commonly occurs due to contaminated injector lines or degraded columns surfaces. Septum bleed can also contribute to tailing, particularly at high injector temperatures. The correct troubleshooting approach is to first replace the liner and the septum. Only if the problem persists should column trimming or replacement be considered. Let's now move on to the opposite peak shape problem, that's the peak fronting. Peak fronting is observed when the front portion of the peak appears sharp and compressed while the remaining portion spreads abnormally. This problem is almost always related to sample overload. When too much analyte enters the column at once, the stationary phase cannot retain it effectively, resulting in fronting. This issue is not due to instrument malfunction, it is purely related to injection conditions. Reducing injection volume or diluting the sample usually corrects this problem immediately. Increasing split ratio also helps limit the amount of sample entering the column. Now that we have discussed peak shape distortion, let's move to another issue where peaks appear normal but become unusually wide. Broad peaks indicate loss of chromatographic efficiency. This problem usually develops gradually and is often overlooked initially. Low carrier gas velocity slows analyte movement, leading to peak spreading. Improper oven temperature, especially very low initial temperature, can also prevent proper focusing of analyte at the column inlet. In some cases, column degradation reduces efficiency permanently. To correct this problem, first verify carrier gas flow using a flow meter. Then optimize initial oven temperature to ensure effective focusing. If peaks remain broad even after optimization, column replacement becomes necessary. Now, let us discuss one of the most disturbing GC problems, unstable baseline. Baseline noise is one of the most commonly reported GC issues in pharmaceutical laboratories. When baseline becomes unstable, even properly separated peaks cannot be quantified accurately. In most cases, baseline noise is usually caused by contamination in carrier or detector gases. Moisture and oxygen are the most common contributors. Saturated gas traps lose their ability to purify gases and become a major source of contamination over a period of time. Electrical grounding issues may also introduce noise. Replacing gas traps, performing a thorough leak test, and ensuring proper grounding usually stabilizes the baseline. Sometimes the baseline is not noisy but slowly move upward or downward. Let us understand that problem next. Baseline drift is commonly observed during temperature programmed methods. The baseline slowly increases or decreases instead of remaining stable. The most common cause of baseline drift is column bleed at high temperatures. As columns age, they release stationary phase fragments that appear as drifting baseline. Excessively high oven temperature accelerates this problem. Reducing maximum oven temperature and proper column conditioning may temporarily help you. However, if the drift still continues, column replacement is usually a requirement. Now let us move to a problem that creates confusion even when running blank injections. Ghost peaks are one of the most confusing problems in GC analysis. Even when blank injections are run, unexpected peaks appear. This problem usually occurs due to carryover from the previous samples. Highly concentrated or sticky compounds tend to remain inside the syringe, linear or the column. Inadequate syringe washing allows residual compounds to reappear in subsequent runs. Increasing syringe wash cycles, using appropriate wash solvents, and baking the column at elevated temperature helps remove the residual contaminants. Now let's move to a problem that directly affects method reproducibility, retention time variation. Retention time shift is one of the most frequent question observations during audits. Retention time in GC is directly controlled by carrier gas velocity and the oven temperature. Any change in carrier gas flow due to leaks, regulator fluctuation, or EPC instability leads to RT variation. Column trimming also shortens retention time and must always be documented. Flow verification using an external flow meter and proper leak testing are essential steps to control this problem. Now let us discuss a problem where peaks are present but separation is not adequate. Poor resolution means peaks are not properly separated, making quantification unreliable. This issue may appear gradually as column efficiency decreases over a period of time. Improper oven temperature ramp or excessive sample loading may also contribute to it. Optimizing oven program and reducing sample concentration may improve segregation. However, when the column efficiency is lost, replacement becomes unavoidable. So far, we have discussed problems which are related to chromatographic behavior. Now let us move into injector specific and hardware related failures. Split peaks are observed when a single compound appears as two closely separated peaks instead of one. This problem often creates confusion because analysts assume column damage or failure. In reality, split peaks usually originate from the injector. One major reason is injector backflash. When the injected solvents expand rapidly, it exceeds the linear volume and part of the sample flows backward instead of entering the column uniformly. Incomplete vaporization can also reduce this problem, especially when injector temperature is not sufficient for the solvent used. Improper liner design or wrong liner volume further worsens the issue. To correct this problem, injection volume should be reduced. Injector temperature should be increased appropriately based on the solvent boiling point. Using a liner which is suitable for split or splitless mode is extremely important. Injection technique, especially injection speed, must also be consistent. Now let's move to another injector related issue that silently affects the peak quality. Backflash occurs when the injected solvent expands beyond the volume of the injector liner. This causes part of the sample to flow backward into the injector body instead of moving forward into the column. When this happens, contamination occurs inside the inlet system, including septum, gold seal, and inlet surfaces. Backflash results in poor reproducibility, distorted peak shapes, and unexpected contamination peaks. The risk of backflash increases when large injection volumes are used, injector temperature is low, or narrow volume liners are installed. To correct this issue, injection volume should be reduced. Injector temperature must be sufficiently higher than the solvent's boiling point. Using a larger internal volume liner significantly reduces the backflash risk. Understanding solvent expansion behavior is extremely important in GC troubleshooting. Once the injector contamination starts, another visible symptom which begins to appear is unwanted peaks originating from the septum material. Septum bleed peaks appear due to thermal degradation of septum material. These peaks usually appear at early retention times and may interfere with the analyte peaks also. Poor quality septa or extended usage at high injector temperature accelerates septum degradation. As injector column temperature increases, volatile components of septum materials are released and appear as additional peaks. This problem is especially common in residual solvent analysis, where early diluting peaks are very critical. Using high quality low bleed septa and replacing them at defined frequency is very essential. Injector temperature should be optimized, not unnecessarily high. Poor septum management significantly improves chromatographic cleanliness. Now let us move deeper into column related problems that develop over a period of time. Column bleed, it occurs when stationary phase starts decomposing and releasing material at high temperatures. This appears as rising baseline and increased background noise. Column bleed increases with temperature and becomes more prominent towards the end of the temperature program. Aging columns, oxygen exposure, and excessive oven temperature significantly accelerate the bleed. Once column bleed becomes excessive, it cannot be fully reversed. Reducing maximum oven temperature and proper conditioning may temporarily help. However, severely damaged columns must be replaced to maintain data quality and compliance. Now let us discuss a problem that directly affects the detector signal stability. FID flame going off is a common operational issue during the GC analysis. When the flame is extinguished, detector signal is lost and the baseline becomes flat. Incorrect hydrogen and airflow ratios are the most frequent causes for this. Moisture contamination in detector gases can also destabilize the flame. A dirty detector jet restricts proper gas mixing, increasing flame instability. To correct this issue, gas flow ratios must be verified according to instrument specifications. Detector jets should be cleaned periodically. Only high purity, moisture free gases should be used for stable flame operation. So far, we have discussed injector, column, and detector related issues. Now let us move to gas delivery and system control problems, which often create recurring failures. Gas leaks are one of the most dangerous and underestimated problem in gas chromatography. A very small leak may not trigger any alarm, yet it can completely disturb chromatographic behavior. When a leak is present, carrier gas flow becomes unstable. As a result, retention time starts shifting and reproducibility deteriorates. Leaks also allow oxygen and moisture to enter the system, which gradually damages the column and reduces the detector response. Leaks commonly occur at column connections, injector fittings, detector fittings, or aging gas tubing. A proper leak test must be performed periodically using an electronic leak detector. Ferrules should be replaced whenever columns are reinstalled. Correct tightening technique is critical. Over tightening can also cause leaks. Now let us move to a problem that occurs even when no physical leak is visible: electronic flow instability. Electronic pressure control, or EPC, regulates carrier gas flow in modern GC systems. When EPC becomes unstable, flow fluctuates even though set parameters appear correct. This results in inconsistent retention times and frequent system suitability failures. EPC instability may arise due to sensor malfunction, using electronic components, or communication issues between GC and the software. In some cases, restarting the GC and data system temporarily stabilizes the EPC. However, repeated flow fluctuation indicates hardware degradation. Flow verification using an external flow meter is essential to confirm the EPC accuracy. If deviation still persists, EPC module replacement becomes necessary that time. Now, let us discuss a problem that is often mistaken for method failure but actually originates from the automation. Autosampler related issues are very common in routine GC operation. Inconsistent injection volume directly affects peak area reproducibility. A damaged or bent syringe needle can lead to partial injections or maybe missed injections. Air bubbles trapped inside the syringe barrel also reduce injection volume significantly. Hard or incompatible vial septa may restrict needle penetration, leading to improper sample aspiration. Routine syringe cleaning, correct priming, and periodic replacement of septas are essential. Auto-sampler maintenance must be included as part of preventive maintenance schedule. Now let us discuss a problem where everything appears normal, yet system suitability still fails. SST failure is one of the most stressful situations during analysis. Even when chromatogram appears acceptable, numerical parameters fail acceptance criteria. High RST often indicates injection inconsistency or autosampler issues. Poor resolution and tailing factor failure usually points towards column degradation or contamination. Insufficient column equilibration between injections can also affect the system suitability. Ensuring stable flow, consistent injection, and adequate equilibrium time is very critical. If system suitability continues to fail repeatedly, again after again, then column replacement should be considered. So, friends, finally, let us bring everything together in one practical troubleshooting mindset. Repeated GC failures usually indicate not a single technical problem, but a poor troubleshooting approach. When analysts change parameters randomly, root cause identification becomes impossible. Lack of preventive maintenance leads to gradual deterioration of system performance. Absence of proper documentation makes recurring issues difficult to track. The most effective solution is to follow a fixed troubleshooting sequence: gas, injector, column, detector, and the method. Preventive maintenance schedules must be strictly followed. Every corrective action must be documented so that recurring patterns can be identified. This structured approach significantly reduces repeated failures and investigation burdens. Now, let us conclude this masterclass with a clear takeaway. So, GC troubleshooting is not about guessing or panic. It is about understanding system behavior and applying the logic calmly. Every GC problem gives symptoms. Those symptoms always point towards a cause. When you learn to read those signals correctly, GC becomes predictable and reliable. With structured thinking and good maintenance practices, GC can remain one of the most powerful and dependable instruments in the pharmaceutical laboratory. So, friends, thank you for watching. If this session added value to your learning, don't forget to like, share, and subscribe for more practical industry solutions. Till then, this is Rajesh signing off.